Okay, what was our homework? Homework was preliminary data analysis and research question. Okay. I'll practice. Okay. Good. Why don't you start from Hyunjung? Come forward and present your research idea and motivating example.
I choose the question about dim sum bone.
There is a mic, so you should use that.
Dim sum bond is denominated in Chinese yen and issued in Hong Kong market. This day, I think there are many people expect that Chinese yen is to be revalued, so that expectation leads increase in demand of dim sum bond, because if there is appreciation in Chinese yen, we can gain foreign exchange profit from that. And also, yesterday I read an article about dim sum bond. It's HSBC Bank announced, I'm not sure, but offshore renminbi bond index, and this clearly show dim sum bond is hot issue in financial market. So I choose these questions.
Okay, thank you.
Actually, I changed my research question to
So you should make your Google page public.
I'm not like familiar with the Google system.
Go to share. Here share. And publish to the web. Publish to the web. Automatically publish it. And then delete the link. And then write the stop. No, because I think there should be some click OK. It's hidden. And we can try it again. Okay. And go back and click this one. Okay.
Right. Is it posted?
That
It takes a little time.
okay. Another idea is secret window and yeah. And you can click view and actually you can go to format maybe. No. You can go file. There is a way to get that as a web page. See it as a web page. No. Any. Insert.
Well, I'll just then. Actually, I changed my research question because after some research, I found that Japanese earthquake in Japan actually have not so big impacts on Kospi, so I've changed to more interesting research question to me. So I've decided that I would like to know how much impact like political or religious events have impact on world crude oil price. Thinking of huge impacts of crude oil price on world economy, I think this question will be kind of interesting to me.
Yes, it's interesting.
This is the oil price movement from 1970s to 2008, and you can see the Lebanon conflict and Iraq war and Gulf War. Like you can see the how oil changed dramatically after the crisis in the Middle East.
Next, your turn.
My research question is about how can investors make excess return with the CSR index? And as you can see in the graph, the blue line is the return cumulative returns of CSR index, and red line is Kospi 200. So as you can see,
Could you please explain briefly what you mean by CSR?
CSR is stand for corporate social responsibility. It's kind of corporate invest for their stakeholders like employees or society or everything for society welfare. Actually, my focus is how this investment enhance corporate performance. So what I want to research is this excess return is sustainable, and if it is, how, why, and how can investors make excess return with this CSR index? Yeah, so I think it will be very interesting topic, and it also be this investment strategy will be long-term strategy. So it will be very interesting topic in finance, and it's very due. What I checked is recently 2009 Korea published our own CSR index called SRI index. So yeah, so good. That's why I think it's very interesting topic.
Thank you. That's Hyo.
My research paper is about which developing country can be good to invest, either a country adopting totally open market economy, such as Chile, Brazil, and or a country has a trade barrier such as China and India. I got this idea from a book, Bad Samaritans. That book said developing country need trade barrier in order to develop in their developing economies.
Nothing else to say. Okay, thank you.
Actually, my topic was how peaks affect to the Korean economy, but it was very broad, so I narrow my topics on a FX position and interest rate. In short, how peaks affect the Korean interest rate and the FX position, and how this affects to the Korean economy. For example, when peaks countries are faced to the sovereign risk, and if they are face the default, then Korean because global world are connected, so the Korean economy, Korean interest rates and the FX position will be changed. So by researching this, I can apply it to another case, like a Dubai shock or something like that. So I choose these topics. However, during I researched these questions, most of the data was updated on last year June. It means most of the data are very out of date. So I think it is very hard to apply on these days, but I will try my best. Thank you.
Okay, well, next homework, now you have to get the data next week. Homework for, okay. Homework, this is homework 1, okay. So again, you have to reply to this. Homework 1, set 1 is conduct principal component analysis using column P to I in the data for practice. Data for practice is here. Data for practice. And then plot the time series of the first two principal components. Okay, I'll explain what is principal component. Second, collect data about your research question and do conduct preliminary data analysis like mean, standard deviation, maximum, median, minimum, and variance, covariance matrix. Actually, yeah, correlation matrix. You know the correlation matrix, right? Okay. Any question about next week's homework?
So, can you explain about correlation?
Oh, correlation matrix is like, so suppose you collect data like x1, x2, x3. Suppose they are your data, okay? And then this is basically variable and 1, 2, 3, 4, 5, n. So it is ID for your observation. This is name of x1, x3 is name of your variable. So what I want to do is to draw a table, something like this. So maybe we have to use Excel. So first column is like n. Okay, how many number of observations? Second one is mean, standard deviation, max, mean, and median. Okay, and then through correlation matrix like x1, x2, x3. So basically you have to feel they are 1, correlation, so correlation with itself is 0, right? And they are symmetric, so you don't have to feel this one, and this is correlation between 1 and 2, right? This is correlation between 1 and 3. This is correlation between 3 and 2. So basically you feel this. And if you have like 4 variables, it is you have to fill 6 numbers. So it is close correlation of each other.
We have to use a program like SPSS.
I recommend you to use R, but that is not required. R would be most convenient, but SPSS is fine. Excel is fine as well. You can do everything with Excel.
Is there like equations to calculate the correlation?
In Excel or
Well,
in R?
are in do they have functions? functions?
Yes. So like again, like R correlation, okay, and R correlation coefficient is R. So D is the data. So simply CORR and D, like something like this. You tell Korean. Yeah, 피어슨 상관계수, something like this. Right? Yes, partial correlation. So everything is partial correlation. Oh, this is too. Anyway, please use the CORR in R. Okay. CORR. COR. Yes, I think COR is the right one. So, like X equals C1, 2, 3, and Y is, I'm not sure whether this is right or wrong, but and correlation X and Y, let me see, 0.05. How about covariance? This is interesting, okay. Oh, what is this? Yeah, anyway, you know what I mean, okay. So let us continue last week's topic. So they are again, they are all the proxy for the sentiment. As I told you last week, since I cannot measure sentiment of investors directly, what I instead did is I collect data that is possibly correlated with sentiment of investors, right? And I try to extract some information from those proxies, and they are list of proxies. So N list is number of listed company. So my case is that when people market sentiment is high, there will be more supply of the stock. Okay, more and more firms want to be listed in the exchange because investors are happy. So N list is possible proxy. And second of all, implied volatility. Implied volatility is sometimes called fear index. It measures people's perceived uncertainty. People's perceived uncertainty about the future. So maybe there is a negative measure of the sentiment. The higher volatility, maybe the lower sentiment. And third one is momentum. So momentum is, it is in the existing literature, people don't regard momentum as a sentiment index, but I actually asked the people in YHYU and what kind of sentiment index they use, and many people, many fund managers says that they regard sometimes momentum as the sentiment proxy. So I decided to include it. Next one is a foreign investor, and foreign investors often regarded smart investor, and they, if they are smart, they may want to exploit the sentiment of the investor or lead the sentiment of the investors. So maybe the behavior of the foreign investor may include some information about the sentiment of the market. So I included it. And KKR is the Kospi 200 index divided by Kosdaq index. So depending on whether people are happy or not, sometimes they prefer maybe small stocks, sometimes they prefer large stocks. So I included it. ETF is discount rate of the ETF. So it is ETF market price minus ETF net asset value. So actually, it is in the existing literature, people use discount as a closed-end fund, closed-end fund to measure sentiment. But since in Korean market we don't have closed-end fund data, so instead I use ETF data. Okay, so when people are happy, people will buy more and more ETF, more. So maybe the value of the ETF compared to the underlying value of the true value of the ETF maybe deviate, maybe narrowed. And if people are unhappy, then discount of ETF may be larger. So I included have core ratio. Food is basically betting about the dismal future. Core is the bet on the optimistic scenario about the future. So by investing a ratio of how much people invest in put or call, something about the sentiment. And then percent of the stock that is above 20-day moving average. So stock that is outperforming may measure investor sentiment. Again, it is not in the existing literature, but practitioners regard how many stocks are above long-term average. They regard that as some kind of sentiment, so I actually included there. And stock turnover. Stock turnover is how basically measures how often people trade. When people are happy, they are likely to trade a lot. Unhappy, they are not. Therefore, maybe trading behavior may contain some information about the sentiment. And the closed-end fund discount, we don't have data about this. And IPO, they are all related to IPO. So IPO is similar to the first one, number of stocks listed, number of firms listed in the exchange. So IPO means basically firm offers new stocks to the market. Therefore, when firms think markets are happy, sentiment of the market is high, they are likely to provide more stock to exploit their opportunity. That's why I included IPO activities. Okay, as a proxy for sentiment. Last one is log ratio of the market weighted average market ratio of dividend payers and non-dividend payers. So basically, I compare the stock price of dividend payer and non-dividend payer. Yeah. And I won't investigate the stock market, but some stocks are very similar to bond. Some stocks that pay a lot of dividend, right? They are more similar, although they have stock, they have more likely to bond feature. Like bond, they pay coupon and those stock pay dividend. So the more dividend they pay, those stocks is more likely to behave like bond. And my guess is that when people are happy, when people's sentiment is high, they are more likely to take a bet on the stock. When people are depressed, maybe they don't want to do the betting on the stock, so maybe they want to invest more on bond-like stock. So price difference between dividend payers and non-dividend payers may contain some information about the people's sentiment. Agree? Okay, so they are the data. So basically they are, these all things are the data I could get, and these X things are the data I could get. So what I did is that I collected this sentiment for proxy for the sentiment, right? And the next step is somehow I have to combine those information in order to extract underlying sentiment, right? So they are all proxy for the sentiment, which means that when people's sentiment change, they will move all together. Of course, like ETF discount or IPO, they may affected by other like regulatory or institutional factor, possibly, right? So what I want to do is I want to extract the factor that affect all those sentiments altogether, and I want to remove other information that's irrelevant to the sentiment, right? Do you understand? So again, my strategy is somehow I want, so they have all those variables and good theoretical background about why they are the proxy for the sentiment, which means that if there is some powerful underlying factor, although we cannot observe, if there is powerful underlying factor that moves all these values together, that must be a sentiment, right? Yeah, it should be, right?
Yeah.
Because they're proxy for the sentiment, and I agree that they are influenced by other factors. But I am only interested in common factor that all move all those proxies all together. So I need some kind of a statistical technique such that the statistical technique, by analyzing behavior of all those variables, the statistical technique could extract common factor out of this series of the data, right? That kind of statistical technique is called the principal component analysis. Okay. So I apply principal component analysis to given data, and principal component analysis extract the common factor, and I define that common factor as a sentiment. I'll explain to you how to do the principal component analysis, and it is your homework. Okay, actually, until next week. Let me skip this. Okay. So basically, this is the result of my principal component analysis. So out of this data, this is actually better. Okay. Okay, somehow I did principal component analysis and I extract the sentiment. Okay. And then I want to check whether the sentiment makes sense or not. Right? So through the principal component analysis, I extract the sentiment index and I check the correlation of the sentiment index with underlying other proxies. So this is basically, this line is the correlation between the sentiment index constructed from principal component analysis with proxies. The first turnover and the sentiment, it has very weak relationship. And then what? Yes, foreign is a very strong correlation between foreign investors' behavior. Right, so it makes sense. When foreign investors comes to Korean market, maybe there is the high sentiment in the market. That makes sense. And it takes discount, it is negative, so it is again in line with theory. And trading volume and sentiment is negative relationship. Okay, that is a risk strategy. And momentum and sentiment is positive relationship. So that makes sense. Actually, in your homework, what I want to do is develop some table to extract this, okay, with your own data. And let's take a look at the graph. So the red one is sentiment index I constructed from principal component analysis. So with ETF discount, and then what else? Yes, especially implied volatility. My sentiment index moves a lot with implied volatility. And sentiment index moves negatively related to momentum. And sentiment index has again negative relationship with implied ownership of the polygons. And then the one most interesting thing is the last one, COSPI 221. Right? And if we compare this red one, sentiment, and this black one is cumulative return from COSPI 200. And it seems like they are negatively correlated. So they look somehow related to each other, right? So it means that maybe our sentiment index has some information about future of KOSPI 200. So this picture suggests that there may be a way to exploit our sentiment index to make money with KOSPI 200 index. And in order to investigate that possibility, basically what I did is I did regression. I did regression about to invent the relation between sentiment index and then KOSPI 200 return. So in this case, basically, this is kind of independent variable, and this is kind of regarded as a dependent variable. So it's more to find the relation between sentiment t minus 1, yesterday's sentiment, actually it is weekly frequency. So sentiment 1 week ago and sentiment today, market price today, it is KOSPI 200, and it is the relative performance of the small firm over big firm, and relative performance of the high booked market ratio firms over low booked market ratio firms. So high booked market ratio firm is called value firm, and low booked market ratio firm is growth firm. So this one is actually relative performance of the value firm over growth firm. And this table shows that sentiment clearly has some predictive power about market, right? Market portfolio, which is KOSPI 200, and small firm over big firm, and the value firm over growth firm. Okay. So this suggests that when sentiment is high, it means that tomorrow maybe market price will go down because it is negative correlated. And when sentiment is high, maybe small firm underperform over big firm because it's negative. And it means that value firm underperform big growth firm. So this suggests how to make money. And actually, this result is in line with our previous theory. So when people are happy, when sentiment is high, it means that when sentiment is high, people are maybe more likely to invest, like engage in stock investing. So it will boost up. When people are happy, it will boost up the stock price. Right? But sentiment always changes. Therefore, when sentiment drives the stock price today, expected stock return until tomorrow will be low. Right? That's why maybe we have this negative relationship between today's sentiment and tomorrow's market price. It is more risk market return. There is actually market return over risk-free rate. Okay. And this one is exactly the same argument. When people are happy, sentiment is high because they are happy, pleased. So they will more likely to invest in small stock rather than large. They have more interest in the small stock, and that will drive up the price of small stock relative to large stock. Right? Which means that there is possibly bubble in the small stock over large stock. So as a rational investor, if we want to make money, we have to do opposite strategy. Right? When people are happy, we have to sell small stock and buy large stock. That's what is negative relationship says. And when people are resistant, when people are happy, maybe they will rather high book-to-market ratio stock, high value stock, which are depressed stock, and therefore they are likely to invest in more. Okay. Yes. So this is high minus low. So let's test. So this statistical relationship shows that maybe sentiment index has information about not only our market performance about the future, but also relative performance of the small stock over large stock and value stock over growth stock. So actually this graph shows what I did. So this graph shows that my strategy is when sentiment goes up, therefore my strategy is when sentiment goes up this week, maybe people are happy, so they are more likely to invest in stock market. So when people's sentiment goes up, then today I sell stock. When people's sentiment go down, then I buy stock. And I want to test how much profit that makes. Okay? And this black one is the performance of my strategy, and this red one is Kospi 200 performance. And as you can see, the black line consistently beat the red one, which means that our strategy can make profit by this amount. This is a similar, so green one is actually when people are happy, I sell small stock and buy large stock, and then in addition to that, I sell value stock and buy growth stock. Okay, so it is like not asset allocation between stock and cash, like market over risk free. It is a relative change or relative weight between those stocks, right? Even that strategy can generate significantly positive return over this value, which is cost 200. Which means that again, our strategy, investment strategy makes sense. And in addition to that, it means that if we combine this market over cash allocation, okay, if we combine this black line and this green line, then our performance will be even greater. Right? Which means that we can make even larger profit out of this trading strategy. And this is actually size of the trading strategy. So compare our those market over cash trading strategy. I compare the trading profit of the trading strategy with cost 200, and on average, weekly, our strategy generates profit of 0.3%. On the other hand, cost P beat risk-free rate only by 0.12%. So it is almost 3 times of the cost P 200 performance. And actually, my strategy has even lower standard deviation. And I applied multi-factor model. So I checked relative performance of my portfolio return over risk-free rate, and I regressed that on the market factor and size factor and growth factor, which are usual factors in multi-factor model. And I can find significant alpha. This significant alpha, and this is alpha. So it is like 0.21% per week, and it is equivalent to almost 12% per annual. Which means that if a fund manager apply this strategy to their fund management, basically they can generate 12% of the excess return over their portfolio. And which means that this strategy, if fund manager applies, ignore any other strategy and only apply this strategy, still the fund manager would be like a top 5 fund manager in the entire industry. Again, so this performance is equivalent to the top 5 fund managers' performance. And this is the portfolio based on not between market over market and risk, not about investment market one. It is investment strategy between small and large stock and value and growth stock. So it is given market portfolio. I just change weight between small and large and value and growth. Still, even after taking into account all the usual risk factors, my alpha is about 0.144% per week, which is equivalent to almost 8% per year. So again, it's maybe the top performance in the market. So this result, actually, and this my result always take into account the transaction cost. When we sell or buy stock, we have pay some fee, right? And actually this performance is after the transaction cost. So even after taking into account the transaction cost, my strategy can generate this high amount of excess return. So in conclusion, our tactical asset allocation upon investor sentiment can generate excess return even after adjusting risk through standard risk model and transaction cost in Korean market. And second, in addition, the asset allocation generates extra performance whether we use valuation fluctuation of the market portfolio or cross-sectional fluctuation of the individual stock. The valuation fluctuation of market portfolio means I determine it is my decision problem of whether to enter into the market or not. But cross-sectional fluctuation means determining change of the relative weight between small and big firm and growth firm and value firm. Okay? And it is thought that it will generate enhanced performance to combine allocation strategies about both level and cross-sectional variation of the stock. In my paper, I only showed this cross-sectional strategy and the level strategy separately. But if we combine those strategies together, then you can imagine how much profit we can make. And finally, we have used only crude trading strategies for robustness and easiness. My trading strategy is very simple. I simply buy or sell depending on the size of the investor sentiment. Very simple. And if we can, of course, apply more sophisticated trading rule, surely we can make higher profit, even more profit. Yeah, this is it. If you are more interested about this my paper, actually you can go to this SSRN and you can download my full paper. Full paper, and actually this is my core with some quantitative analysis in Samsung Asset Management, and you can click and you can download my paper. And this result is so good, okay, so good that they are trying to make a 적립식 fund, like a mutual fund, out of this strategy. Okay. So in this class, you will come up with also your own trading strategy that can possibly help other investors. Okay. Now about homework, let me go back to this one. One of the important steps of this paper is actually this one. Okay. Okay, extracting principal component analysis out of the variable. So in our homework, what you can do is first you click server error, okay? Then you can download the data for practice. Actually, this is data you have already analyzed. And homework is conduct principal component analysis using the column B to I. So using the column B to I, out of these variables, I want you to do the principal component analysis and extract the most important factor, which should be sentiment, and second most important factor, I don't know what it is, but anyway, extract those principal components and plot the series of it with R. Okay. And about the principal component analysis, if you are interested in, of course, if you are curious about principal component analysis, of course, we can go to Google, like Yes, and then there are a lot of explanation about principal component analysis. There is even Korean version. 예, 데이터 집합을 분석하는 기법 가운데 하나이다 등등등. Okay. Principal component analysis is a mathematical process that uses an orthogonal transformation to convert a set of observation of positive correlated variable into a set of uncorrelated variable called principal component. Something like this. Okay, and in R, principal component, command for principal component is basically princom. Yeah, princom. So you can do help. Princom, and then in R you can go to help menu about principal component analysis. Princom and X, and then some formula. Okay, so there is even example, so you can try. And then in addition, actually, I did some Google search. And actually, I found even PPT, PowerPoint presentation slides of a PCA, which is this one. Yeah. And I didn't make it, I just downloaded it. I don't know who made it, but it looks very cool. Even though I make a slide about principal component analysis, I don't think I can make such a good slide as this one. But anyway, let's use this PowerPoint slide to go over the principal component analysis, to learn some theory about principal component analysis. Okay, so what is principal component analysis? It is basically data reduction technique. So it is a summarization of the data with p variables by a small set of k derived variables. Okay, so suppose this is original data. So n is the number of observation, and p is number of variables. Right? So suppose it is about population, and n is name of the people. People 1, person 1, person 2, person 3, something like that. P is like a variable to describe each observation. So it is like height, age, education, something like that. Okay, male, female, something like that. So P is again variable. Names, number of variables, and N is number of observation. And through principal component analysis, basically we want to reduce data like this. So instead of looking at all the variables of P, by just looking at smaller set of variables, K number of variables, basically we want to transform data from this to this. Okay? If we transform data from this to this, to K important value, of course, it makes our life much easier, right? Now we have only K number of variables to analyze. In many marketing analysis, people choose K equal just 2 sometimes. Of course, by reducing the P number of variables through K, we will lose some information, of course, right? But through the principal component analysis, we want to make sure that we lose as little information as possible while we reduce the number of variables. Okay? So basically, principal component analysis means that somehow we reduce number of variables from P to K, okay, by constructing K most important variables and summarize this N data, N observation with K most important variables. Principal component analysis is basically extracting the K most important variables out of P. Yeah, it is exactly the same thing what I did in the analysis, right? I collected some proxies, right? So in my sentiment analysis, P is the number of the proxy and in my analysis k is 1. I just collect one most important variable out of this, and I define that as a proxy for, I define that as a sentiment because I collected proxy for sentiment, and if there exists the most important underlying factor, that should be the sentiment. Any questions now? So conceptually, principal component analysis is very simple. Again, in my example, my P is number of proxy, which is actually 9 in my paper, and K is 1. And in your homework, you have to make a K equal 2. Data reduction. And residual variation is information in A that is not retained in X. Right? So if we select K out of P, it means we lose some information. Right? Out of that, the lost information is called residual. So residual variation in information A that is not retained in X, so it is thrown away. And this is basically balancing act between clarity of representation, ease of understanding. So if we have a small number of P, right, we have a clear clarity in representation, and it is much easier to understanding if we have a small number of P. But instead, if we have too small number of P, it is kind of oversimplification possible. Right? And loss of importance of possible relevant information. So the more, when P is close to K, we solve this problem. But we have this problem. When P is close to, P is a small number, we have this advantage, but we have disadvantage of this. So it is important to what should be the size of P in our data reduction technique. In principal component analysis. So principal component analysis is probably the most widely used and well-known of the standard multivariate method. And it is invented by Pearson and Hotelling. Oh, I didn't know that. It is first applied in ecology by Goodall under the name factor analysis. You all know Goodall, right? Goodall is a very famous biologist. So principal factor analysis is synonym for PCA. Principal component analysis takes the data matrix of n objects by p variables, which may be correlated, and summarizes by uncorrelated axes. Principal component or principal axes that are linear combination of original p variables. So if we go to the first page, what happened to the P is equal to K? If P is equal to K, actually we don't lose any information, right? It's just, if P is equal to K, we simply reordering of the variables. In the principal component analysis, in addition to that, when we consider K number of principal component variables, okay, we want to combine this P variable such that the selected K principal components are not correlated with each other. So again, principal component analysis means that we want to reduce P number of variables into K number of variables, such that these K number of variables are not correlated with each other, independent, orthogonal to each other. And then the first K components display as much as possible of the variation among objects. So again, principal component analysis is that when we select K out of the P, we construct the P such that K such that the variables in K are not correlated with each other, and the ordering of this K variable such that the first one is the most important one, the second one is the next important one, like that. And the geometric rationale of the PCA. PCA objects are represented as a cloud of endpoints in a multi-dimensional space with an axis for each of the p variables. So we have n observations and we have p number of variables. And we want to change this one into the and in this notation it is k, right? For each of the p, it doesn't matter, okay? It doesn't matter. P1 and yeah, P. So this is k, p. Stick to the original notation. So we can regard this k number of variables as the axis. Okay, they are the axis. So if k is only 2, then we have 2 orthogonal axes. And this each one is like observation, so we can practice observation in the 2 orthogonal axes. Yeah, axes. The centroid of the point is defined by mean of each variable. And the variance of each, it is same to centroid, is same to mean that we already know. And the variance of each variable is the simply average of the squared deviation of its n values around the mean of that variable. It is already what you know. And the geometric rational PCA again, the degree to which the variables are linearly correlated is represented by their covariance matrix. So it is simply a definition you already know, is covariance. And objective of the PCA is therefore to rigidly rotate the axis of the p-dimensional space to a new position, principal axis, that have the following properties. The p-principal components are ordered such that principal axis 1 has the highest variance, axis 2 has the next highest variance, and axis p has the lowest variance. So in this case, actually, k equals p in our previous example. So we order original number of p variable into the another way, such that each ordered variable is orthogonal to each other, and the order of each other, the first one has the biggest variance, and the second one is next biggest variance. So first principal component is most important, and second one is next important, like that. And they are ordered such that principal axis 1 has the highest variance, axis 2 has the next highest variance, etc. And covariance among each pair of the principal axis is 0, which means they are orthogonal to each other. So it is graphical example. 2D example of the PCA. So suppose this is original data. So maybe this is it is maybe education level, and maybe this is level of age, education level and age, and maybe we have data looks like this. Okay? It's natural. We have the more age, the more education possibly. So the data looks like this. And then in order to understand the data more easily, what principal component analysis does is we define this axis and this axis again. Basically, we want to rotate the axis. So the new figure looks like, so yeah, here various variable x1 and x2 have positive covariate and each have a similar value, right? They are indeed positively correlated each other, and they have similar values because the minimum and maximum, the distance is similar to the same. Right? And what the principal component analysis does is, okay, this is mean of x1 and x2, and variance of x1, variance of x2, and covariance of x1 and x2. Okay, and what principal component analysis does is first we match the center. Okay, so now this is point 0 and 0, so we demean all our data. Right? So we make our data, the mean of our data is 0 for each axis. And then each variable is adjusted to a mean of the 0. subtracting the mean from each value. So it is like demeaning. Okay, and then second, once we demean, then we rotate, right? We rotate this one around this origin. So we want to make first principal component has a maximum value. So the maximum values occur through this axis, right? So we rotate it like this way. So if we do the rotation, the data would be look like this. So with the new principal component, we have a representation of data looks like this. So this one actually assists us interpreting the data, right? Because yes, this one has maximum variation with this one, and this second variable has orthogonal to each other. So they are independent of each other. These two principal components are independent of each other. So we can analyze data better with this axis and this axis than the previous, right? So the information, or the location of each point, basically, are more informative, basically, by reading the point through this axis and this axis. PC1 has the highest possible variation, which is 9.88, and PC2 has a variance 303. Okay. PC1 and principal component 1 and principal component 2 has zero covariance. Okay, so it is basically geometrical interpretation of the principal component analysis. And the dissimilarity measure using PCA is Euclidean distance. Okay. So in many marketing analysis, actually, what marketing people do is they collect two principal component analysis and plot data looks like this, and next they usually do the segmentation analysis. So they make segment, they define this one as one segment, they define this one as second segment, something like that. The intuition is that when they collect those data together, they measure the distance between the 2 points as the Euclidean distance. Right? So when we say one point is closer to each other, basically we measure the distance through Euclidean distance. Right? We measure this distance as a Euclidean measure. Right? PCA uses Euclidean distance calculated from the p variable as the measure of the dissimilarity among the n objects, and PCA derives the best possible k-dimensional representation of the Euclidean distance among the objects. When Euclidean distance is basically measure of distance you already know. You already learned in high school. So suppose you have these 2 points. Suppose you have these 2 points. What is the distance between the 2 points?
x2 minus x1. And the square of height. Plus y2 minus y1. And then square root of
Right, exactly. This is called Euclidean distance between the 2 points. And in principal component analysis, Euclidean distance calculated from p variables are the measure of the similarity measure. So in practice, nobody uses PCA with only 2 variables. The algebra for finding principal axis is readily generalized to the p variable, and PC1 is the direction of the maximum variable in the p-dimensional cloud of the point. So in our graphical example, basically we have only 2 variables, and we just rotate the 2 variables. But in practice, we have maybe more than 2 variables, and we summarize that variable with a smaller number of variables. And PC2 is the direction of the next height variance, subject to the constraint that it has the zero covariance with PC1. And the PC3 principal component 3 is of course in the direction of the next highest variance subject to the constraint that it has zero covariance with both PC1 and PC2 and so on up to PCP. If we have P number of variables, we can maximum F. We can extract only P number of variables. So PC1 and PC2, each principal axis is a linear combination of the original two variables. Right? So here, Y is basically PC analysis means mathematically speaking, Y is basically original variable. So what we do is basically we take a linear combination of the original variables and make to define new principal component. And A, I, J in this example are the coefficients for factor I multiplied by the measured value for variable J. So principal component is just basically simple. Suppose if we have n number of variables, and suppose we want to summarize the n number of variables into only two number of principal components. Principal component, what we want to do is PI2 PI2 is so principal component 1, 2, so actually let's say this I and this principal J, and this is A, J, and Y, and something like this. And principal component analysis means that suppose I is 1 and J is 2. What we mean is that we wanna find this coefficient from AI1 to AJN. We want a coefficient such that these new variables are independent of each other. And if I is greater than J and I has a larger variance than this one. If I is 1, it should be the maximum possible variance out of this. If I is 1, then it means that we should find from A11 to A1n, we should find A such that this newly constructed P1 has maximum possible variance. And other one, P2, P3, should have the next possible largest variance, but should be orthogonal to the first one. And the PCX are with rotation of original variables. And the PC1 is the simultaneous the direction of the maximum variance and the least square line of the best fit. Squared distance of point away from PC1 are minimized. So by definition, so PC1 is the possible is the line the possible largest variation, which means that the PC1 is a regression line of the data. Because PC1 should be able to fit the data most, should be able to explain the data most. And generalization to the P dimension, if we take the first K principal component, they define the first K dimensional hyperplane of the best fit, the point cloud. And of the total variance of all P variables, PC1 is the PC1 to K represents the maximum possible proportion of the variance that can be displayed in K dimension. Right? So in fluctuation of data, in variation of data, this clearly shows that in principal component analysis, when you choose K principal component, the K principal component should be able to explain the most variance, most possible variance out of all variance. And I is the squared Euclidean distance among points calculated from their coordinate on PC1 to K are the best possible representation of their squared Euclidean distance in the full P dimensions. And covariance versus correlation. So using covariances among variables only makes sense if they are measured in the same unit, and then variables with high variances will dominate the principal component. So therefore, actually we have to use correlation. This problem is generally avoided by standardizing each variable to unit variance and zero mean. So intuitively, principal component analysis means that we want to find the variable that can explain most possible variability in the data, right? So basically, when we wanna do, if we wanna do principal component analysis, we have to analyze correlation or covariance structure between each variable. What if we use covariance if we analyze covariance instead of correlation, we have a problem because by simply multiplying constant to one variable, actually we can arbitrarily inflate the influence of that variable, right? And we don't want that. We want everything standardized. So the best way to standardize everything is d-mean and divide everything with their own standard deviation. Which means that, which is mathematically equivalent to that instead of analyzing covariance, we analyze correlation matrix among the variables. Right. So covariance between the standardized variables are basically called correlation, as you know. And then after standardization, each variable should have has a variance of 1, standard deviation of 1. And correlation can be also calculated from the variance and covariance like this. So once we have covariances, then actually we can recover correlation. Or write a more familiar formula, basically. Correlation between ij, right, is very I think this formula maybe looks more familiar to you. Yeah. And the algebra of the PCA. Okay. First step is to calculate the cross product matrix of the variance and covariance among every pair of the P variables. And then square symmetric matrix. And diagonals are the variances, up diagonals are covariances. So this is typical covariance matrix, and this one is the covariance between x1 and x1. Covariance between x1 and x1, therefore it is basically variance of the x1. And this one is covariance between x1 and x2, and which should be same covariance between x2 and x1. And this one is covariance between x and x2 and x2, so it is basically variance. So it is variance of covariance matrix. And therefore, diagonals are all variance and up diagonals are covariance. Correlation matrix, which is part of your homework, is like this. In all diagonal terms are 1 because it's correlation between itself, with itself, so it should be 1. And then this is the correlation between 2 and 1, this is correlation between 1 and 2, and therefore they should be same. So it is called correlation matrix. And basically, principal component analysis analyze either covariance matrix and correlation matrix to find the relation of each variable, to extract most important part, to drive what generates the co-movement of these all variables. That's kind of principal component analysis. So in matrix notation, this is computed with S equal xx, and x is the n multiplied p data of the matrix with each variable centered, and manipulating and transposing. Could change the columns to row and row to the column, okay? And multiplying matrix, you already know how to do it. And some of the diagonals of the variance covariance matrix called trace, and it represents the total variance in the data. The trace in the matrix notation, trace is simply sum of the diagonal. And so trace of this matrix is simply 12.909. And this actually 12.909 is the total variance in the data. In this case, its trace is 2. Okay. And it's actually mean squared Euclidean distance between each object and the centroid in p-dimensional space. Right? Because this diagonal comes, so this one is basically, this argument is basically this term. And the second one is this term, right? And if we add them all, this is basically square distance. And if we put this square root, then it really becomes the distance. Right? Because everything is centered, so everything is measured from the origin, right? So basically this is x1 and y1 is integrated 0. Right? And finding the principal axis involves eigenanalysis of the cross product matrix S and eigenvalue of SR solution to the characteristic equation. Could you please raise your hand if you never heard of the eigenvector or eigenvalues? No? Okay, no, sorry. Don't you know the eigenvalue and eigenvector? It is a very important part of the matrix algebra, and if you learn linear algebra, you will surely learn the eigenvalues and eigenvectors. And basically, principal analysis is basically eigenvalue decomposition. Okay, anyway, let me try. So the definition of eigenvalue looks like this. Okay. So I is basically identity matrix, and S is arbitrary matrix, and this part is basically determinant. Right? So the solution of this equation or lambda is called eigenvalues. So therefore, suppose we have a matrix like a 2, 0, 1, 1. Okay. Suppose this is S. And to calculate the eigenvalues, we have to make S minus lambda I equals 0. Right? And if we do this one, then basically what we want is 2 minus lambda 0 is 1 minus lambda, and determinant of this is 0. Right? And the determinant is, as you know, it is a right? So the eigenvalue is basically 1 and 2. You all remember how to calculate 행렬 결정식, right? 행렬 determinant. They are called eigenvalues of a matrix, and eigenvalues are unique to any squared matrix. When you hear eigenvalues, lambdas are called eigenvalues, and then the algebra of PCA. So by using this one, similar operation, actually we can calculate eigenvalues of this matrix. Okay. And eigenvalues are, first eigenvalue is 9, and second eigenvalue is around, first eigenvalue is around 10, and second eigenvalue is around 3. Okay. And interestingly, the sum of the eigenvalue, which is 12.9091, is basically the same to the trace of the matrix. And so again, trace of any squared matrix, not any squared matrix. Trace of this variance covariance matrix is exactly the same to sum of those eigenvalues. So what does that mean? So basically trace of the variance covariance matrix measures total variance of the data. But therefore, sum of eigenvalues measures total variance of the data as well. Okay? Because trace is basically Euclidean distance of each point from the origin, right? And basically that is exactly also the definition of the variance. And that is same to the size of the sum of the eigenvalues. So sum of the eigenvalues is basically measures total variation. The eigenvalues lambda 1 to lambda p are the variances of the coordinates of each principal component axis. So interestingly, okay, eigenvalues are unique, right? Eigenvalues are unique. So principal component analysis basically means that we want to make matrix such that, okay, the eigenvalues we want to find appropriate coordinate corresponds to each eigenvalues. Right? Again, eigenvalues, some of the eigenvalues are some of the basically same to the total variance, and eigenvalues are unique. So basically principal component analysis are basically or finding eigenvalues and change the order based on order of the eigenvalues. We can find appropriate coordinate of each value, right? Because eigenvalues are unique. So if we can find the coordinate that it corresponds to the largest eigenvalue, that is first principal component. If we can find the coordinate that is corresponds to the second largest eigenvalue, it is second principal component. Second principal component. The sum of the all p eigenvalues equal the trace of S, which is again the sum of the variance of the original variables. Now each it doesn't explain eigenvector. Actually, eigenvector is also important. Now eigenvector, since we know eigenvalues, and actually we also have to know eigenvector. So eigenvector, we can find eigenvector once we find eigenvalues. Okay? Eigenvector is such that so S is original matrix and lambda is eigenvalue. For given eigenvalues, eigenvector solves this one. So this is X is eigenvector. So given eigenvalues, we can find this X. So in the previous example, this covariance matrix has two eigenvalues. And for each eigenvalues, we can find the two eigenvectors like this. Two eigenvectors like this. And actually, eigenvectors are not unique because whenever we multiply any constant to this x, it is also the eigenvector, right? Because it satisfies each equation. So since eigenvectors are not unique, when we find eigenvectors, the most common way of finding eigenvector is to normalize eigenvector such that the Euclidean distance of that eigenvector is 1. Right? So in this case, I'm pretty sure that the coordinate, the distance of this eigenvector from origin is equal to 1. It looks like 49, 36. I think they should be close to 1. I think. So each eigenvector consists of the p-values which represent the contribution of each variable to the principal component of the axis. So if we have, okay, this is in the variance covariance matrix with p number of variables, we can find the p number of eigenvalues. Therefore, we can find the p number of eigenvectors. And each eigenvector is basically the contribution
right? Basically, the contribution of each variable to the principal component axis. So eigenvectors are basically uncorrelated. When we construct eigenvectors, actually eigenvectors are all uncorrelated. So by definition, we can regard that as a coordinate. It's a coordinate of the direction of each principal component. Yeah. So in this case, eigenvalues are also going to each other because we multiply this and add, multiply this and add together to become 0. So these two vectors are also each other. And the coordinate of each object I on the case principal axis is known as the score of the principal component K and are the computed as this one. Okay, here V is the n by K matrix of the PC scores and X is n by P centered data matrix. So U is P by K matrix of the eigenvectors. So basically this means that geometrically this means that okay so X is basically data. We represent the X data X. We represent that as a new coordinate. So each eigenvector becomes a new coordinate. So we measure, so basically it is a way of rotating the data. So given the previous, we want to transform the previous rotate into, we express that as with a new coordinate, which is represented with eigenvectors. And the variance of the scores on each principal component axis is equal to corresponding eigenvalues for that axis, therefore, and the eigenvalue represents the variance displayed by the case axis, right? And then the sum of the first k eigenvalues is the variance explained by the k-dimensional organization. So basically, in your homework, when you calculate the first and second principal component, basically what you have to do, you have to find the score. It means you have to find the score of the each principal component. So since in the homework I want you to extract two principal components, which means that you have to find the score of the PC1 and score for PC2. Yeah, this is an example. So trace is PC1 explains. In this case, okay. So total variance, as I told you, sum of the eigenvalues are the total variance of the data. And the first eigenvalue is 9.8 and second eigenvalue is 3.0. So total trace is 12. So 12 is the total variance. And first principal component basically explains the fraction by the first eigenvalue. So in this data, the first principal component explains as 76.5% of total variance. Okay. Because it is a ratio between the first eigenvalue and sum of the all the eigenvalues. And as you can guess, the variance covariance matrix between principal components should be looked like this, right? First, the correlation and covariance between the two different principal components are 0 by our construction. Right? And then the covariance between the principal components should be equal eigenvalues, which is again in line with our definition of the principal component. 0 and eigenvalues. And more challenging example, so I think it is I don't know who made this slide, but the developer of this slide must be a biologist. So it is basically data from research on habitat definition in the endangered bobo frog. Okay, so it's bobo frog data. There are 16 environmental and structural variables measured at each 112 sites. So there are 124 observations, and in each observation there are 16 environmental and structural variables. And the correlation metric used because variables have a different unit, right? Each environmental factor and structural variable have very different units. So instead of using covariance matrix, maybe we want to use correlation matrix. Okay, so they are the eigenvalues of this matrix. So there are 16 variables, so which means that there are 16 eigenvalues, but they show only 10 eigenvalues. This is percent of the variance. So basically, percent of variance is, as I explained, it is a ratio between this value and sum of all the others. And this is cumulative of the variance, so it is ratio between all sum of all the eigenvalues and eigenvalues up to this point. And interpreting eigenvectors, and I think this is eigenvectors, and correlation between variables and principal axes are known as loadings. Okay, so in my previous analysis, okay, very correlation. In my previous analysis, so this part is the correlation between my sentiment index, which is first principal component, and their proxies. So these numbers are called factor loading. I calculate factor loading with correlation matrix. Okay. And these factor loadings are in these slides is this one. So they are factor loading. And if we take a look at the factor loading very clearly, actually we can interpret the principal components. So if we take a look at this one, so this one is the principal component 1, 2, principal component 3, and these are correlation between principal component and individual variable. And this red one has large positive value, so which means that first principal component is related with, I don't know, somehow location, right? I'm not a biologist, but it looks like a distance. And first one is like altitude height. So first principal component looks like location on some site, right? And it's about second principal component. I don't know what, but it is related with relief. I don't know what. I cannot interpret because I'm not a biologist. And third principal component is related, positively related with both, okay, and negatively related with pH. I think it maybe somehow correlated some moisture, okay, the extent of the water in the air. And so first one is like location is amount of the water, and this one is, I don't know what it is, but anyway. So we have another environmental variable, so basically we summarize number of environmental variables with a couple of smaller things like location, water, and something, I don't know what. And each element of the eigenvector represents the contribution of the given variable to a component. Okay. How many axes are needed? And it is a technical question. So when we summarize P number of variables into K number of principal components, then the question is, what should be the size of the K? Right? In my sentiment analysis, given my research question, K is 1, which is obvious, right? Now, in many cases, sometimes it is not easy to determine number of principal components, and actually there are several rules. The most popular rule is this one. So basically,
we can basically measure the importance of principal components with the size of the eigenvalues, right? And by plotting this eigenvalue, first eigenvalue should be largest, second one should be second largest. So we can basically plot eigenvalues like this. And this value 1 is usually cut right. So in this case, we have 1, 2, 3, 4. 4 principal components as eigenvalues greater than 1. So in this case, many people choose only 4 values to summarize data instead of 10. So usually this one is a cut right.
And what are the assumptions of PCA? I don't think we need this. Assumed relationship among variables are linear. Yes, that's natural. Yes. Okay, don't think it is necessary. So we have very quick, usually the statistics or applied statistics department, they learn principal components over several weeks, but actually we learn in less than 1 hour. It's very quick. But anyway, in the next class, after the break, I will illustrate principal component with an example with R. So maybe you can get a better idea about principal component analysis. Okay, let's take a 15-minute break. So let's briefly review the principal component analysis. Okay, so this is usual Euclidean space, and this is 0.1, this is 0, right? And these 2 points, 0, 1 and 1, 0, this denotes the direction of this axis, right? So anything, if we multiply any constant to this one, basically constant to this one denotes basically this axis, right? But usually we want this vector plus this length of this vector to be 1. We want to make it 1. So this is 0, 1 is the usual way to denote the x-axis. And 1, 0 is the usual way to denote y-axis. This is the usual high school math. And those two are orthogonal to each other, right? Which is 90 degrees, pi over 2. This is mathematically, it means the inner product of these two vectors are 0. So 1, 0 multiplied by 0, 1, no. 1, 0 and 1 is 0, right? So inner product of these two vectors are 0, which means they are orthogonal to each other. Okay. And our principal component analysis means basically okay. Before we the principal component analysis, so about this axis again, so it is 0, 1. No, it is 0, 1, right? And if we want new coordinate, something like this, right? And one easy way to represent this coordinate is to find the point that such that the distance of this one is 0. So for example, if it is the angle is pi over 4, then this point would be something like this. So this
new vector. This vector denotes basically the direction, right? Direction of the actually denotes basically new axis, which is 45. The angle is 45 degree. Okay. So what principal component analysis means is given the variance covariance matrix of this one. So it is not convenient. So suppose we have variance covariance matrix. It's not any more complicated. Anyway, let's use this. Suppose we have variance covariance matrix of this one, and if we want to do the principal component analysis with covariance matrix, although you have to do covariance analysis, principal component analysis with correlation matrix, but if we use covariance matrix and if it is given covariance matrix, what we want to do is basically we want to find new covariance matrix such that this is transformed into the first eigenvalue and second eigenvalue. So by combining x1 and x2 appropriately, by multiplying some constant to x1 and multiplying some constant to x2, and by adding them to, basically we can define new vector, right? And by defining new vector, which is PC1 and PC2, PC1 and PC2, PC1 and PC2, basically we want linear combination of these x1 and x2 to find the new vector, new value of PC1 and PC2, such that their variance, okay, their variance is exactly first eigenvalue, and variance of the second principal component is the second eigenvalue, right? And their covariance is all zero, right? So principal component analysis again to transform this covariance matrix into this one, and to transform from this to this, we have to find the PC1 and PC2 such that they are linear combination of elements. And geometrically, it means that geometrically it means that we want to measure the location of this new data set. Okay. Previously, our data is measured in terms of x1 and x2, right? But now we want to measure new data with new axis, with PC1 and PC2, right? And the new axis, PC1 and PC2, can be represented with their own eigenvectors, right? So their own eigenvectors. So this is their eigenvector. So in this new eigenvector, basically we want to rotate such that, so this is original x1 and x2, right? Original x1 and x2, and we by combining linear combination of x1 and x2, we define new coordinate such that u1, and now we have u1 and u2. So previously we have 0, 1 and 0. Now we have new coordinate such that u1 is like 0.7 and 0.6 somewhere here. This is one coordinate for PC1. And this is new coordinate such that like -7 and somewhere here, right? -7 and from 7, something like this. So new coordinate looks like this. So previously our data is somewhere like this, and how we measure the data with this axis. Now, given new eigenvectors, with eigenvector we define new coordinate, and we measure the location of existing data with this coordinate. Okay. So that's the intuition of physical component analysis. And In this case, we have only two variables. In this case, we have only two variables. In more general case, we have like p number of variables, which means that we have p number of eigenvalues and p number of eigenvectors. Right? So we have a p number of new code. But by making k smaller than p, basically we summarize p number of variables with k selected principal component. Which means that we ignore eigenvalues, eigenvector outside of those selected k number of the eigenvalues and eigenvectors. And when the usual rule of thumb is that when we choose those k number of eigenvalues and eigenvector, we select those eigenvalues and eigenvectors such that eigenvalue is only we select those whose eigenvalues are greater than 1. That's usual rule of the thumb. Okay. Any question? Now, let us do some practice with R, principal component with R. Okay, and then I appreciate. Say that R. Okay, and then PCA.R, and then open with okay, and then I already made some code. Set working directory c temp source pca.r. Try. Good. Okay. Okay. The first what is going on? 4 columns. So our new data looks like this. So basically you can regard this as a data such that we have this one. So first the principal component to basically capture this and this by multiplying point 0 and point 0. And second principal component is basically first one and get the negative. Add basically this one and this one and this one, or and basically subtract this one. So first principal component is basically this one and this one. Second one is basically we wanna remove this part, right? And third principal component is basically we take into account first this and this, and fourth principal component is actually I don't think these two are anyway important.
Anyway, by investigating the factor loading, we can basically guess what those principal components means. So by investigating factor loading, basically first principal component is basically linear combination of second and fourth variable. And let's get the scores. And we can calculate scores. And scores is they are the principal component. They are the principal component, right? So this scores is first principal component is looks like this, and second principal component looks like this. So basically, so these and these are homework. You have to extract in some sense. So first principal component, this one is basically this factor loading is 0.7, 0.7. So this first one, this one is basically this data multiplied by 0, this data multiplied by 0.7, and this data multiplied by 0, and this data multiplied by 0.7. So it is like 1.44, and third one is it is close to 0, and yeah, something like that. And then let me check whether they are correct principal component. So let's define this one as data S, and if we multiply S, T transpose of S, I forgot how to, it is matrix algebra, it looks like this, and S, if we do S multiplied by S, it is round 2. This is too difficult to read, so it looks like this. Scores. This. Okay. This course Varimax plot. Okay. Course. 1, 2, 3, 4. Course. Oh, I forgot the syntax of the R. No. T. Okay, 8.8333, and then a eigen no, it's eigen values, standard deviation. Yes, they are the standard deviation, and they are the eigen values. And then score, they are same. Okay, they are same. Scores. help print comp principal component. Okay, so the argument, formula, data, subset, correlation, and detail, value. Okay, standard deviation of the principal component. Matrix of variable loadings. Matrix whose columns contain the eigenvector. Oh, yes, loadings are basically eigenvectors. These are current loadings, the loadings. And center, this means or subtractive scale. Scores true. Score of there are non only vectors supplied and if. That's strange. Ah, okay. I think score correlation true. So, S T, the S is a score matrix. T S S is around 883. What does this mean? So actually these core values are something I didn't expect. So I think about more what does this value mean. But anyway, let's compare this principal component analysis with eigenvalue decomposition. Okay. So as I told you, basically principal component analysis is basically eigenvalue decomposition such that we want to measure, we want to redefine each data, each observation in terms of new axis. New axis is all defined with new eigenvectors, right? So basically, in R, actually we can also do the eigen analysis. So suppose we want to do the eigenvalue, get the eigenvalue of the correlation matrix, then we can simply type eigen and the correlation matrix of the data. Okay. So this is basically, we have eigenvectors like this, and then we have 1, 2, 3, 4. Yes, we have this is our eigenvector, and this is our eigenvalues, right? And eigenvalues are basically variance of each principal component. So basically, the square root of these eigenvalues should be equal to the standard deviation of each principal component, right? So let's put only values. This is eigenvalues, and the given eigenvalues, let's do the calculate square root of these eigenvalues. and we have these numbers, right? So they are square root of the eigenvalues, and this should be equal to the standard deviation of principal component, and we can check S&P, PCA, and then STEV, right? And they are same, right? Therefore, the eigenvalues, each eigenvalue are square root of these eigenvalues are basically standard deviation of each principal component. And then let's compare these eigenvectors. Okay. Let's loadings, and then these eigenvalues and the vectors, right? Eigenvectors. So yes, if we compare this and this, actually not easy to see. So we need to do round up to 3. Right? This looks like this, and again the loading is looks like this. Right? So basically eigenvector factor loadings are basically eigenvector. Right. So this is an eigenvector. And then actually we can do the plot. Now we have two loadings. So actually we can do the plotting of the loadings of the first two, 1, 2, first two. And if we plot the first two using the first two loadings, and if we do the plotting, then we have something like this, right? So it means that our four variables, our four original variables, we can, if we plot those our four variables with the first two principal components, then we have clear two group of the variables, right? So these two variables are basically can be almost explained with this component, right? And these two are basically clustered together. So basically, we can first two principal components basically group existing variables into two groups in some sense. So with those two principal components, basically this figure, this plot shows that we can summarize four original variables very well. Actually, there is another way. If we can rotate this further, actually which is called the Varimax rotation. So if we do the Varimax rotation, so to slightly this way, then we can match these two exactly to this point. We can do this rotation. Okay, so sometimes we do the rotation like this in order to interpret the data even more easily, right? So rotate, loading. Varimax. S&P loading, I didn't define it, so instead of this one. And loadings, Varimax loadings. yes, rotate the plot. Rotate it. And it's not that different. But anyway, this open plot, this one even slightly further, such that this rotation actually shows the classification of variables even more clearly. Actually, so this is not important, but this is the usual trick to trick we use in order to interpret the data better. I show you every analysis. So yes, rotation and plot rotation. And square root of these eigenvalues are basically, eigenvalues are basically same to the standard deviation of each principal component. And about square matrix, I don't get it. Why the square matrix looks like this? Let me see, score again. Data looks like this. Seven, what? Like this. Okay. Course looks like this. And they are all orthogonal to each other. And then y. Let me see. Okay. This core matrix is scores on PCK. Yes, score on principal component K are computed with data matrix. Yes, we multiply data matrix and then multiply eigenvectors. Data matrix and eigenvectors. Strange. Data looks like this. Eigenvectors. Again, it looks like this. So let's define as this EV like this. So data multi Hey, I'll think about it more about, but anyway, score matrix is something you have to calculate in the homework. So please give the data. Please calculate score matrix and plot the first two columns. The score matrix. So actually, I did the work. Strange. and then if we multiply okay. R principal component analysis. Who are you? 누구야? 자네 누구야?
중에 지금
뭐?
다음 수업
정신이 없네. 아무튼 이 스코어 매트릭스가 내가 원하는 아웃풋이 안 나오는 것 같으니까 I'll think about it. I'll think about it. I'll post my message on the Google. Okay. 네, 아무튼 오늘 어려운 토픽을 굉장히 넓은 토픽을 짧은 시간에 했는데 숙고가 많았고 막판에 내가 원하는 결과가 안 나서 뭔가 좀 이상한데 여러분한테 죄송하고요. 그 부분을 해결해서 올려드리도록 하겠습니다.